Now we come to the two, in my opinion at least, most interesting subsections. The sections about flow control and congestion control. So what is the problem with flow control and congestion control? I mentioned this already in the introduction, that flow and congestion control, they're important. Flow control, not to overload the receiver. And congestion control, not to overload the network. They both together are a really interesting feature of TCP to keep the whole system stable. Okay, so first of all, flow control. What does it mean? You remember sliding window, layer 2. We need a sliding window mechanism. Well, that's what we use on layer 2. We need this, well, to keep track on the already sent packets and the already acknowledged packets. So we can use initial windows, and we saw on layer 2 that if we receive acknowledgements for 3 segments, so 1, 2, 3 is fine, then we slide the window. So that was the idea. So this is similar to layer 2, but now we are talking about bytes. We do not count packets or segments, as they are called on layer 4. We send the bytes and we count bytes. So we shift the window by a certain number of bytes as soon as we have the acknowledgement for these bytes. Window size, and that's quite interesting, can be changed dynamically during the transmission phase. And the window, as we will see, is controlled by, that's flow control, the receiver window we get via the TCP packet, and a so-called congestion window. That keeps track on the congestion inside the network. So that's quite interesting. There is some urgent data. Remember, there's an urgent flag that is all immediately sent, disregarding the sliding window mechanism. So now we talk about the sliding window mechanism, normal data, nothing urgent. Okay, what is the situation? We have on the left-hand side the sender and right the receiver. And now we assume, we start with our connection, a receiver buffer of 4K, and the receiver buffer is empty. First step, the application in this example writes 2Ks into a buffer, the sender buffer, and then the sender starts transmitting the 2Ks. Let's assume we start at sequence number 0. So that's the first byte, is byte number 0, and this fills the receiver buffer with the 2Ks. In this example, no errors, nothing. We acknowledge these 2Ks, and we know this already. This acknowledgement tells us in TCP the next byte I expect is the byte 2048. Plus, additionally, we tell the sender, please be aware, now my window is only 2048 because the 2K already occupy 2048 bytes. Okay, application writes again 2Ks. I transmit them again, starting with the sequence number 2048. But now my receiver buffer is full. We assume the receiver does not consume any data in this example. The receiver then will return an acknowledgement telling the sender, look, everything is fine. The next byte I expect from you is the byte with the sequence number 4096. But now my window is 0. This means the sender is now blocked. So it's blocked and you cannot do anything. This is exactly where I said, okay, we have these timers that might check if this takes too long with this situation, window equals 0. But in our case, it's simpler. The application may read 2Ks, and then the receiver says, okay, buffer release. Yes, we have space again, our buffer, and sends on its own to the sender a packet with window size 2048, because now we have again space in our buffer. That's exactly the space we announce here. So Now the sender can again transfer up to this 2K, but let's assume we just want to send 1K. Okay, that's fine. We start filling the buffer again. So we are not forced to transmit 2K. You should know of a funny thing that could happen. It's called the silly window syndrome. In this setting, we have the receiver full. That's exactly what we had in the scenario before. So the receiver is full. Now let's assume the application reads a single byte. What does it mean? Oh, we have again space. Okay, 1 byte. But the sender now tells, the receiver tells the sender, now, hey, I've got 1 byte. Now again, empty space. The sender could think, okay, then I transmit a byte. TCP is byte stream oriented. New byte arrives and immediately the buffer is full. And we continue this. So this obviously doesn't make sense because look at the ratio of header versus this single data byte. So this is why, to avoid this, the receiver typically has to wait until the buffer is reasonably empty again, whatever this means. So certain percentage, not only a single byte. Okay, though that was just the silly window syndrome. How does a complete TCP session look like? We have a client, now an example, sending a packet, SYN packet, with a sequence number. This is arbitrarily chosen. Acknowledgement, well, we don't have this. There's no useful number in because we cannot acknowledge anything in the beginning. We announce a certain window size and a maximum segment size in this case. The server takes this and then answers. So you see, that's the first step of our three-way handshake. We have our SYN packet. The second was our SYN ACK packet. And now we confirm with ACK equals 3000. We exactly confirm this. So 3000 is the number of the next byte we expect. And we also announce a window size. This window size has nothing to do with the window size before. So both sides announce their receiver window. Remember, if we set up a TCP connection, it's automatically bidirectional. So both sides have their receiver window. Additionally, the server in this case could tell, okay, maximum segment size 1400. So you can decrease this. Third part of our three-way handshake, we send the acknowledgement. We can include data here, but here so we acknowledge, and again we announce our window. In this case, no data transmission. Then we start transmitting data, in this example 1400 bytes, starting exactly at 3000, so that was the next byte we have to start with. So that's our next one. And we acknowledge the by piggybacking, announce our window, and so we can continue until the other side hopefully acknowledges. And you see now how we can acknowledge each of these segments. We can also wait. That's not the point. So we can acknowledge a certain number of the bytes so that the sender then knows everything is fine. And in this case, we don't have a problem here in the receiver, so you don't see any decreasing receiver window. So that's not the point. You just see this ping-ponging of sequence numbers and acknowledgements. Then we can send some data again, and then we can acknowledge this data. We can send a FIN packet to start closing the connection. This is acknowledged by a so-called FIN ACK packet. That means you could also send only an acknowledgement. In this case, also the server closes the connection. This is why it's called a FIN ACK. And this is what we then acknowledge. So that is basically how this classical flow of a complete TCP session looks like. And flow control, that's the flow is controlled by setting the window. So if you set the window to 0, you stop the complete data transmission in one of the directions. Both sides have their windows as you see. In this example, we don't have to decrease the window. And typically it's if you have a certain size of the sending window, typically it's the congestion window that influences this, because this receiving window, the buffers, well, typically they're large enough. So flow control, relatively simple, trying not to overload the receiver. Now coming to congestion control, and that really is the main part of these two interesting mechanisms. This is where it gets a bit more complex. So while flow control, as I told you, adjusts to the capacity of the receiver and is managed by the receiver. This is our window. So if the receiver has only a small capacity, then the receiver sends certain value in this window field, and if you send 0, then you stop the sender completely. Okay, congestion control. We know this is about the network, and congestion control, this is managed by the sender. Or, well, we have many senders contributing potentially to the congestion. So here the idea is somehow all these senders, they somehow have to take care that inside this network, maybe we have a bottleneck link, we do not create congestion. We have one assumption that packet loss, and this assumption TCP has, packet loss is rarely because of transmission errors. It's typically, if we lose a packet, it's due to congestion. Is this justified? In wired networks, yes. In wired networks, you typically, if you lose a packet, this is due to congestion inside the network. This assumption is completely wrong in wireless and mobile networks. But that's something for my lecture on mobile communications. But here in our fixed networks, well, that's a valid assumption that if we lose a packet, then a router somewhere in the network is overloaded. So how does this come together before we have a closer look into this congestion control? So end to end, I said we use a sliding window to control how many bytes we send. And our sliding window is now a sender window that is defined via receiving window, congestion window, and we take the minimum. So receiving window, that is based on the receiver input, as I showed you, how many bytes can the receiver receive without overflowing receiver buffer. We've done this. That was our flow control. Congestion control, that controls the congestion window. How many bytes, again, can I send without overflowing the routers? So this is layer 3 problem. Receiver buffer, that's our layer 4 problem. Congestion is based on network conditions, and this can be observed by the sender. Then on the sender we take both values, receiving window and congestion window, and we go for the minimum. And this is now our sender window. Okay, we've already done flow control, receiving window. Now let's have a closer look into congestion control. So the problem was congestion. Too many sources contribute somehow with their data to the network, and somewhere inside the network we get this congestion. How do we notice? Well, the delay grows, so round trip times increasing time, longer delays because we queue more in the buffers of the routers. And in extreme case, we lose packets because we have overflow in the router. And what does a router do? I mean, if you have a bottleneck link here, you simply drop the packets. That's all. And really solving this problem of congestion is one of the main challenges of the internet, because you can assume, I mean, if too many senders contribute to the traffic inside the network, yeah, you can create an unstable network. Why unstable? You cannot rely on data transmission. Routers will start dropping. Which packets to drop? Is it an important packet or not? So many problems there. Congestion itself is not really a new problem. Today you may think of, oh, we have terabit links. Yeah, but we have also many 4K videos, etc., etc. But congestion happened a long time ago. Mid-80s, internet almost died of congestion. So we had a collapse from 32 kilobit per second to 40 bit per second. That's really a collapse. So today maybe you have a collapse from terabit to some megabit, but that's also a collapse. And when Jacobson invented congestion control, a solution that really directly went into operating system, Berkeley System Distribution, BSD. And yeah, then everyone thought, okay, congestion control is solved, but then many PhD theses, discussions and conferences. And just lately, there are again new discussions about, can we apply some new methods, machine learning, we have new contexts, we have huge data centers, and how can we then control the internet traffic? Okay, so as I said, receiver window, we learned this is for the receiver. Isn't it enough to just look at this? The problem is, I mean, if you just look at the receiver window, what happens? If there's still space left in this window, the node starts sending the full window of packets. Why not? If in our example we had window size 2500, so why not sending, well, for example, 2 segments, depending on the maximum segment size, and filling this window. So this is a burst. So if you send a full window of packets, this creates bursts. Networks don't like bursts of traffic. So, and just think of if, for example, I do retransmission, also after time expiration, immediately I retransmit my packet. So that is a problem. So if you limit the sending rate only by flow control, you always get this burst of packets the size of the receiver window. So you have an extremely bursty traffic with a high probability that if 2 bursts arrive at the router will start dropping packets. So that's really a problem. Okay, so what could happen? I mean, what is this congestion, this collapse, and how can this happen? So the endpoints don't have a certain look into the network without any additional mechanisms. Endpoints, receivers, senders, they do not know anything about what's going on. All I see is I experience delay. So my round trip time goes up. Okay, so I measure the round trip time, as I told you with the timers, I measure this, I sample the round trip times, I smooth it, etc. So the packets are more and more buffered at the routers, so the round trip time goes up. The problem is, if now the round trip time exceeds our timeout for retransmission, the host starts retransmitting packets. How clever is retransmitting of packets due to congestion? What happens? You increase dramatically the congestion. So, well, I mean, if a car doesn't arrive due to a congestion on the road, just send a new car, and yet another, and yet another. So retransmitting because of a timeout is not really a brilliant idea if you have congestion. So because then this increased traffic will lead to more delay, leading to increased traffic, leading to more and more delay, and then we retransmit and retransmit and retransmit. And what happens is, for example, if we transmit our data here across this network, and we have here a shared buffer here in the machine, because we have several data streams and they cross a router somewhere in the net. So we have the other connection also crossing here. Then we will see that depending on the network load, first of all, the throughput, the overall throughput will go up. It will go up. But also delay will go up. And then there's a certain point where really we have a delay that might be too long, and then the timeout triggers and we start retransmitting. If we retransmit, the throughput, so what we really can use, well, doesn't increase that much anymore, because the retransmission, I mean, this is doesn't really contribute to the throughput. So it contributes to the load, but not the throughput. Then delay starts going up because of the more traffic, until we reach a certain point where we only have many retransmissions, a lot of packet drops, and then basically the network collapses and delay goes towards infinity. So that is a problem. So we have to do something here. Okay, so what do we want to solve? Congestion control tries to solve three things. Number one, we try to estimate the data rate that we can really use. Often in this context we speak about bandwidth, but you should all know, no, this is not our hertz, our spectrum. So we have to find out what's the bottleneck. So how do we adjust our signal flow to the bottleneck bandwidth? If you assume we have routers, many routers, and we have our path through the internet, then we have somewhere the destination, somewhere our source, we have to find out, maybe this is our bottleneck. So what is the data rate we can push over this bottleneck? Because this bottleneck determines the overall data rate from a sender to a receiver. So that is quite important. So we have to estimate our bottleneck. Then we have to be aware that the bottleneck also changes. So can we adjust? Can we somehow adjust to variations of this bottleneck bandwidth? There will be always a bottleneck somewhere, but it's not necessary that it's always the same link. But that doesn't matter. It's always the weakest link we have along the path. And this may change and may vary. So we have to adapt. And then the third goal is, how can we share the data rate we have here in this bottleneck, especially, but overall among the different flows without overloading the network. So if we have, for example, 3 times 10 megabit per second, and those 3, they want to squeeze over a single 10 megabit per second link, fair is something like, okay, all we get something around 3.3 megabit per second. So that's something we assume is somehow fair. So can we somehow reach this fairness? Okay, so congestion control has to do a lot. It's a bit more complex compared to flow control. What do we need so we can actually perform congestion control? We need 2 things. First of all, we have to be able to detect congestion. How do we detect congestion? We cannot just look on the network or ask each single router what's going on. Could be done theoretically, doesn't scale. And typically operators, they don't let you asking the routers. So detecting, and if we detected congestion, we have to react. So first of all, detection. There are different ways how you can detect congestion in the network. 3 approaches Well, one approach is the network tells you. Okay, so the network somehow tells the sender that there's too much going on. Okay. The problem here is network layer 3. The source layer 4. So if we do so, we violate the layering principle. So we even tighter couple layer 3 and layer 4 somehow. So this conflicts also with this really end-to-end idea. What was this idea? Layer 4 is about end-to-end processes transmit data to other processes, no matter what kind of underlying network layer 3 to 1, whatever we have. But it's one approach. The second approach is, okay, we measure really the delay. You can do this, and you can then try to find out what's going in the network, but it's a quite noisy signal. So delay, that you have a large variation there, and so it's not precise, and it's a lot of effort really to measure this. But that's one way of at least trying to detect, oh, there's something going on. There's a third approach that's quite straightforward. If we have a loss, well, that's the most extreme sign that something is going on in the network. And remember, we assume that a loss indicates congestion. True in fixed networks, not really true in mobile and wireless networks. There can be some other reasons for loss of packets. Why is this a good approach? Well, TCP already has to detect this for retransmission. So retransmission automatically detects a loss. And if we assume loss, okay, is caused by congestion, well, loss of packets is a good signal for this congestion control. So these are different approaches we can take. We see in real systems two classes of channel approaches. One is network-assisted congestion control. What does it mean? The routers, they know when there's congestion in the network, they start providing feedback. Okay? So to the end systems. They could tell something like explicit rates, or they could indicate congestion. And this indication of congestion, this is something different communication systems do, but there's also a solution for TCP for this. That's called early congestion notification. And this approach is then really what you saw on the slide before, our approach number 1, where you mix layer 3 and layer 4, because here layer 3, as we will see, tells the higher layer that something is going on. You'll see this on the next slide. The other general approach is that we stay on layer 4, so that's only on layer 4, and this is why we call this end-to-end congestion control. There is no explicit feedback from the network, and we infer the congestion from the observed loss or delay. This would be our approaches 2, delay, and 3 from the slide before. And this loss, that's the important indicator for the original TCP. So the original TCP stays on layer 4, does this end-to-end congestion control by observing loss, a signal we get anyway. There are new versions of TCP that mix the layers, and they do this early congestion notification. So first of all, this network assistant congestion control in TCP. That's this early congestion notification. It's a bit newer, and it's not supported by all endpoints, so check out with Wireshark if you see this bit. So where do we have bits? Well, if supported, then the endpoints can tell the network that they support early congestion notification. And if you look closely to IP packets, so that was the last chapter, you see there was this differentiated service code point and 2 bits for ECN, early congestion notification. And these are exactly the 2 bits the sender can set in IP packets, indicating the network that the sender supports this early congestion notification by setting this bits in the IP packet. So sender, we want to control congestion on layer 4, but now sender uses layer 3 to tell the network on layer 3, I understand ECN. And as the packets travel through the network, if we are in congested areas, what does it mean? Routers notice there's too much traffic on my outgoing link. The routers mark the IP packets. So a congested router sets both ECN bits in the IP packet. So we have 2 bits and we set both ECN bits. And this signals congestion. Well, to whom? It signals congestion to the receiver. Okay, so the sender tells the network, okay, I'm capable of, this early congestion notification. I set this in the layer 3 packets. This is why I tell it the network. And now layer 3 tells the receiver that there was somewhere congestion. Receiver has to do something with this, as you will see. So what is the alternative for routers? Well, if I'm really congested, I can drop packets. But maybe before I start dropping packets, I could mark my IP packets with, hey, there's a lot going on. So as the packets travel through the network, they get these marks, these 2 bits set. Okay, if the receiver gets this IP packet with these 2 bits set, the receiver then echoes back this congestion to the sender. So the receiver tells back the sender on layer 4 that something is going on. So the sender tells the network, so layer 4 tells layer 3, hey, I know how to use this ECN. The network's routers set these ECN bits on layer 3, telling the receiver, hey, there was congestion. But the cause of the congestion is the sender. This is why the receiver on layer 4 has to signal back to the sender, hey, there's congestion. On the way from you sender to me receiver. So you echo back the signal. And this is where we use this ECE flag in the TCP header. So this is ECN, this congestion control echo flag. And now what should the sender do? The sender actually confirms this by setting the CWR flag, congestion window reduced. So then the sender tells back the receiver with this CWR flag, yeah, fine, okay, I reduce my congestion window. So the receiver knows, okay, the sender is aware of the congestion. That is roughly the idea. The big advantage now is this approach distinguishes between packet loss due to congestion or due to a loss on the link layer. So this is fine, but this violates this end-to-end paradigm. So now TCP really explicitly needs IP. But to be honest, this is almost always the case. So TCP always needs IP, checksumming, etc. So you cannot separate TCP and IP. So you don't have a real layering here. So they're really interconnected. So we now have an influence of layer 4 to layer 3 and layer 3 to layer 4. And there's an RFC showing the benefits of this early congestion control. So that's the network assisted control. There's also the second version is the end-to-end congestion control. So typically we check for dropped packets. So we detect the losses. That's what we need anyway for the retransmission. And then we see, okay, what's going on? We see by receiving acknowledgements, we see if there was a loss. So if we get repeatedly duplicate acknowledgements, we see, oh, this was just a single segment. If we don't get any acknowledgement, we get a timeout, then there's something really wrong going on in the network. So duplicated acknowledgement, that's mild congestion, maybe some segments lost, but at least it's a sign there are still packets that make their way through the network. If I have a timeout, that's really severe. So because timeout, typically you have multiple consequent losses. Well, so this approach stays on layer 4. That's so that in the end is pure layer 4, but we can now not distinguish between packet loss due to congestion or due to a loss on the link layer. How should we? So if there's a loss on the link layer because we have short service interruption, wireless link, mobility, etc., that causes packet loss or congestion. So we cannot distinguish these two. So that really is a problem. Okay, so two ways of detecting congestion. Now, how can we react? No matter how we detect congestion, we have to react. So in early congestion notification, yes, the sender tells back, yeah, CWR, we reduced the window, but how? How can we reduce this window? So typical congestion control, which is then end-to-end, not the detection. Detection can be based on network, so layer 3 and layer 4, or only layer 4. The real control is then we are back on layer 4. Now we are end-to-end congestion control. And in general, the idea is we start increasing the transmission rate, so this window size, our sending window, and we probe for usable bandwidth. Remember, one goal was to find out the bottleneck. Okay, so we increase our transmission rate and try sending more and more until loss occurs. That's really telling me, oh, congestion, that's one of the assumptions, or I receive this ECE flag telling me, oh, now there's congestion. There's an algorithm I will explain next. This algorithm is based on additive increase, multiplicative decrease. So we are a bit more careful increasing our data rate, but if something happens, we decrease much, much faster. So how is this done in TCP? Additive increase, we increase our window, congestion window, by 1 MSS, our maximum segment size. And remember, this is signaled. So we increase this window by this maximum segment size every round trip time. This is why it's so important to determine the round trip time. We do so until we detect a loss. So this is this, well, slowly sending more and more, which you will see is not that slowly, but coming back to this. So we increase it. If we detect a loss, we cut the congestion window in half after the loss. That's the multiplicative decrease. So we do not decrease by 1 MSS, but we simply cut it to half. So much faster. So how does this look like? In the end, we get this, what we call sawtooth behavior, probing for the bandwidth. So our congestion window, well, we start at a certain value, but we try, starting from a value, we try increasing until we have packet loss. We take the value and cut it in half. So that's quite conservative. So cut it to half, and then we start again. Additive increase. If something happens, a loss, we cut it to half, and so on. So we probe for the bandwidth, and we can also adapt if something happens in the network. So that is the idea for this congestion window. So what happens now at the sender? Well, as an overview, I mean, we have our congestion window, but we still also have the receiver window. And what we have to take care is that we check for this minimum of congestion window and receiver window, with typically congestion window being smaller than the receiver window. Receiver window, this depends on the buffer, how much buffer space we have left at the receiver. And we have to take care all the time that our last byte send minus last byte acknowledges are less or equal the minimum of congestion window and receiver window. So last byte sent, you send your bytes, maybe not acknowledged, and you have your last byte act, and then you have to look at the difference. So these are basically what is still outstanding, not acknowledged data. So that's the idea. So we can do a little bit of math and calculate the data rate. So looking at the round trip time and knowing this congestion window, so assuming the congestion window is smaller than the receiver window, then we can calculate this rate as congestion window divided by round trip time. That's a rough estimation. Congestion window is dynamic and depends on the network congestion, as the name implies. And as I said, we know that the sender perceives congestion via detection of a loss event. And loss, well, timeout, that's quite obvious, that's quite extreme. Or if we have more and more duplicate acts. So that's also one of the rules. And then you reduce this sending rate. So how the congestion window evolves now is, well, regulated by 3 mechanisms, as I will show next. We have this additive increase, multiplicative decrease. I will also introduce slow start and congestion avoidance. Because, as you will see, this congestion control mechanisms evolved over time. They haven't been in the TCP from the very beginning. So this evolved. So now let's have a look into, because up to now we've looked into this increase and decrease. Now let's have a look into slow start. So let's assume when we start the connection, we start with a congestion window of 1 maximum segment size. So for example, 500 bytes. Okay, so we have 500 bytes, and then we have a certain round trip time, maybe around the globe, 200 milliseconds. And we start with a certain initial sending rate. We can roughly calculate if we send, those bytes, round trip time. The problem is, typically my link has a much larger capacity, much higher data rate. So typically my available throughput is much bigger than this simple calculation, sequence size divided by RTT. So we have to ramp up quickly to a bigger data rate. So that's the idea. So to be too conservative, to let it grow just a little bit, that's not fast enough. So we have to ramp up quickly. And one solution is, let's have upon initialization, an exponential grow until the first loss event. And that's one of the core ideas of TCP slow start. Slow start exponentially, does this go together? Well, yes, faster would be just send the complete receiver window at once. So definitely it is slower than that. But still, you have to ramp up really quickly to the data rate. So how does this work in TCP, this slow start mechanism? So first of all, that's the first phase. The sender has to initialize the congestion window to this MSS, maximum segment size. And the receiver window, well, that depends on the receiver on the other side. So host A knows the receiver window from host B. After connection setup, you know the maximum segment size, and this tells me how big the congestion window is. So what you then do is you start a segment with this MSS bytes of data. And after that, we enter the slow start algorithm. What does it mean? As soon as an acknowledgement arrives before timeout, so that's good. I mean, if something arrives, the ACK arrives before timeout, that's good. So this is a sign that everything is fine. So we assume no congestion. If it's before timeout acknowledgement, that's good. Then, well, we can do a bit more, so we double the congestion window. That's the idea. If not, we reset it to the initial value. Okay, so the slow start algorithm starts with this and continues then with this growth. Each time I get an acknowledgement before I have a timeout. That's the idea. And the growth of the congestion window stops when I reach the flow control window size. Yes, because then I have a problem with the receiver. So we start sending one segment. We get typically within one round trip time the acknowledgement. So that's the idea, telling me everything is fine. Then I double the congestion window, because hopefully I'm still within the range of my flow control. I send two segments. And now, and this is important to understand, for each acknowledgement I receive within time, so first acknowledgement for the first segment, second for acknowledgement for the second segment, for each of this I double the congestion window. So for these two acknowledgements I can double it. The result is 4 segments. For the 4, again, I can double for each of the acknowledgement if everything is fine. Okay, doubling it. And this is the exponential growth, because you double for each of the received acknowledgements if they are received before we have a timeout for this segment. And so this is a bit faster. So we ramp up now exponentially. That's the idea here with the slow start algorithm. So we start with a single segment, and for each ACK I double my congestion window, but the limit is the flow control window. And we always take the minimum. So if, depending on the buffer size, there's sooner or later a stop. So that's the slow start idea. I will show you in the end how this then all looks together. We also try to avoid congestion. So you will see there are several refinements of the algorithms. So for example, introducing a threshold. What does it mean? Well, if we go all the time quite aggressively with an exponential growth, you can imagine, pretty soon will cause congestion in the network. So there's a certain threshold, and that's one of the refinements, that we set this threshold to 64 kilobytes. And the idea now is that the congestion window increases only linearly if we cross the threshold. Linearly, that means for each ACK we receive in time, we do not double, but we only add 1 MSS each time. So this is not as aggressive as exponentially all the time. It's only exponentially up to a certain threshold and then linearly. And in case of a timeout, so something happened, we will also modify the threshold. And the threshold is then set to half the maximum window size. So we have a current maximum window size, and we set the new threshold to half of it. That's the idea. The congestion window itself is set back to 1 MSS. I will show an example that illustrates this. So that's one of the refinements. There's another refinement. If I receive 3 duplicate ACKs, so ACKs indicating that at least something is going on, we cut the congestion window in half, and then it grows linearly. Why? 3 duplicate ACKs interpret as mild congestion, so at least something still goes through. But the timeout is really a severe situation because, well, maybe we don't receive or we don't get any packets anymore. So there's more the need to reset this because maybe we've been too aggressive. So how does it look like if we do this slow start mechanism, slower than just, well, sending a burst of a receiver window? So we try to approach the capacity of the network and additionally try to avoid congestion. So if we all bring this together, you have the situation as shown here. What does it mean? Well, you have certain transmissions of our segments. On the x-axis, on the y-axis, you see the congestion window. Overall, the sending window is derived by the minimum of congestion window and our receiver window. Receiver window not shown here, assuming that the receiver window is much larger, which is true in most of the situations. So how do we start? We start, as I said, with 1 segment of MSS. So for example, 500 bytes or 1400 bytes or whatever. So we start with this 1 segment. We send this, and then we actually receive an acknowledgement, now doubling our congestion window. So the congestion window in the beginning was 2K, and now we double it to 4K. Now we send again our messages, maximum segment size, and for each ACK, positive ACK for the segments, be aware we still count bytes, we don't ACK a segment, but we ACK bytes, we double our congestion window. So after 4, we go up to 8, to 16, to 32. So this is, well, a slow start, although exponentially, but it's much slower than just starting somewhere up here immediately and bursting out the traffic. So we don't do this. Okay, so we ramp up exponentially, so it's a fast utilization of the free capacity, but we don't try this to extreme, so we do not continue, because then exponential growth, that's quite a lot. So up to a certain threshold, and this is our threshold here. That's the threshold value here, and from this point on we grow only linearly. That's our congestion avoidance phase. So we avoid congestion, because continuing exponentially, that's too extreme. So for each received ACK, we do not double anymore. We add one message sequence size, so maximum segment size, our 2Ks. So that's the idea. We add them and then we grow. Now, 1400, 500 bytes, depending what the MSS is. So we increase here and we try to find out the bottleneck data rate. And then it happens, we have a real timeout. A real timeout, so for a transmission. And this means, oh, now we assume at least we have a congestion situation. And this means several things. One is we drop the congestion window to 1 again. So we assume now the overload, we reduce the rate. And additionally, we set the threshold to half the current window. So our congestion window, we simply divide it by 2, and that's our new threshold. What does it mean? Well, be a bit more careful with the next attempt. That's the idea, because the next time we start again, ramping up exponentially, but this time only to the new threshold, and then we continue linearly. The idea is, over the long run, we can perfectly match our bottleneck data rate. Additionally, as we will see, we can also create a fair share of the connection, but only in the long run. And this, by the way, is one of the problems of TCP. Stability, all these mechanisms only work in the long run. They do not work for short-lived connections. Not at all. Okay, so that's the idea of slow start and congestion avoidance. So we still have a problem. And one of the problems is this timeout. If a timeout happens for one single segment, slow start immediately goes back to this only congestion window equals 1 MSS. So slow start is not really well suited if I lose only one packet as depicted here. So you see host A sends several packets and well, yes, one segment is lost in this example. We still receive an acknowledgement for the first segment. We don't receive anything for the second segment. The problem is, the timeout periods are typically relatively long. So, well, timeout, well, we can discuss this. Round trip time is a bit too fast, but so 2 times the round trip time. So at least there's a kind of a long delay before I resend the lost packet. So what happens if I only have a very brief interference? Because a wireless link, so just some packets dropped. And the idea there is that we perform something called fast retransmit. So, because as you see in this scenario, the host B will send back acknowledgements for the segments 3, 4, 5, still acting based on the very first one, what host B expects. It's the second segment. Doesn't have the second segment, but you get back these acknowledgements. And the idea here is the receiver now sends these duplicate ACKs because they all, well, they are all look the same. All these ACKs, they all look the same. They are all duplicated, because we have first one really telling something new, the host, and now we have duplicated. And the idea is that the sender sends out this duplicate immediately when out of order segments arrive. So that means immediately as the host B sees, oh, there's 3, okay, but 2, that's missing. That's exactly this one. Then you immediately send out an egg, and if the next one arrives, immediately send out the egg. Immediately send out these eggs. And now the rule is if the sender receives 3 duplicate eggs, then it says, okay, there really is something missing, and then it resends the second segment. So that is the idea. And why does it help? Hopefully, the acknowledgements, this repeated segment, arise before we have a timeout. Let's start then to slow start. So the hope is that here we get our acknowledgement, the egg for the second. In our case, if we have in more, we can already egg the last segment, but we will get the acknowledgement before we have a timeout for the second segment. And then we do not start with the slow start again. So slow start will never notice this because we never have a timeout. That's the idea. And this works pretty well to recover from single packet loss. So if you just lose a packet and then you get these duplicated eggs, you resend it, hopefully within time, and then you don't get a timeout. It depends on how you set the timeout and well, how fast you can really retransmit. You can even enhance this a bit more to adapt better in case of congestion. And this is then called fast recovery. So we have fast retransmit. That was the idea, just showed in a slide before. Now we have fast recovery. And this fast recovery says, okay, if I receive the third acknowledgement, we actually reduce the threshold. Now calculate maximum threshold halved or 2 times MSS. So that's the idea. Plus we retransmit, our fast retransmit, the missing segment, and we set the concession window to a certain value, our threshold, plus 3 times maximum segment size. So that's the idea. And then we continue. For each subsequent duplicate egg, we increment our concession window by 1 MSS, because it tells me, okay, I still receive something, but be cautious. And that's the idea. Yes, if we have a timeout, then we have to go back to slow start. What's the idea behind is, let's try to skip the slow start phase if slow start is not necessary, because we don't have a real severe congestion. So that's the idea. So we try to stay here with the congestion window, but if it continues, okay, at least we set the new threshold value, and then we go into this additive increase. So that's one of the ideas. So you see, we have several ideas how to actually perform this congestion control. And yes, you could do even without, but this creates a lot of dropped packets. This can create congestion. This makes the network unstable. But as you can also see is that there are several ideas around congestion control, and you can still continue to do research there and to publish your papers and trying to optimize. A lot has been done there. So an overview what you can do, and as the sender, what the action is, you see here on this table. So depending on which state you are, if you are in the slow start phase, so remember, slow start, that's what our exponential growth compared to congestion avoidance. Then, well, you see what happens if you receive an acknowledgement for previously unacked data. That's how it should be. Then you can adjust the congestion window, and sure, you have to check always for the flow control. And if you're beyond a certain threshold, as a thresh, then you go into congestion avoidance phase. So first this exponential grow and then this linear grow. What is the idea here? We double the congestion window every round trip time. So this is why we can ramp up quickly. After that, we are a bit more cautious. So we simply add for each acknowledgement maximum segment size, and this creates our additive increase every round trip time. Okay, that's our linear phase. What happens if we, no matter if we are in a slow start or congestion avoidance phase, if we detect loss by triple duplicate ACK, telling us, well, yes, something was lost, but it's not that severe, we still receive something, then as we saw, we always go to this congestion avoidance phase. If we are in, we stay there. If we are in slow start, we go to congestion avoidance phase. And we try to have, then this will result in our fast recovery, because we know, okay, everything is, well, not perfect, but still it's not that extreme. And this is our fast recovery. If we have a real timeout, then we really have to go to slow start and starting again. If we have duplicate ACK, then we don't change. So we just check, okay, we are not still there at the triple duplicated ACKs. We can discuss why 3 times, why not 4 times. You can do a lot of measurements there showing benefits, pros and cons for different approaches. You can do whatever, as long as you keep the format of the header and the protocol. It's TCP, but it can behave in a different way. And that's also one of the reasons why we have several different flavors of TCP. TCP optimized for certain purposes. So it's not the case that all TCP implementations behave the same. So there are differences. So a summary about congestion control. So if I'm as a sender, with my congestion window, I'm below a certain threshold, I'm in a slow start phase, I grow the window exponentially above the threshold. We try to avoid congestion, so a bit more careful. We grow linearly. If I have 3 times the duplicated ACKs, I do certain actions. So I set the threshold to congestion window half, set the congestion window to threshold, but I don't start with the slow start. Again, if I really have a timeout, if I really have a problem, then I can go back to slow start. You can also do it a different way. So there are new approaches with early congestion notification, even introducing extra new bit, EA bit in the TCP header. You can do this also a different way, and you see that different TCP version, and they differ in this congestion control. TCP Tahoe, you have this triple duplicated ACK followed by slow start, fast retransmit, but no fast recovery. TCP Reno, fast retransmit and fast recovery. We have TCP Vegas, New Reno, Data Center TCP, and some more. They can work together. Yes, they're compatible, but maybe not with the optimal throughput. Maybe also their behavior when it comes to congestion is different. But there are optimizations as well as a TCP for wireless domains. Or TCP if you know that we have short-lived connections. And when I come to QUIC, I will show you that maybe a complete different solution is the solution for certain applications. So I told you that this is a bit more complex, this subsection about flow and congestion control, but you should know what determines the flow of data in TCP. And what is the focus on? Well, flow control and congestion control. What is the difference? What do I mean by congestion collapse? So why can this happen? What can we do against it? How do we actually detect congestion on layer 4 with TCPs? And there are different solutions with their pros and cons. Please do use Wireshark and check if you see early congestion notification ECN with the flags ECE and CWR on transport layer, and the ECN bits set really at work. How can we react to congestion as TCP? And what is slow about slow start? And how do we detect mild or severe congestion? What's the idea of fast recovery? So why can we recover in a faster way? And why don't we have to use then the slow start? And then the final question, can you create your own TCP? No, just do how you like when it comes to congestion control, flow control. What do you have to obey to be compatible? And where do you have certain freedom?